Hello guys, welcome back to my channel. First of all, I would like to apologize. So very sorry for the part 2 for the modern technologies in the data warehouse topic. There is no part 2 video because I didn't did it. I didn't do it. I think that the topic is very short about the data visualization in data warehouse. I think most of you can Google it, and there are plenty much information about that. So I think we're going to move on the next chapter, which is this is the last part 3. Okay, in building the big data warehouse things. Okay, we're going to start with this chapter 6, integration of big data and data warehousing. Okay, previously, there are several issues in the current data warehouse environments that need to be addressed, and more importantly, the current infrastructure cannot support the needs of the new data on the same platform. Okay, this issue we have discussed previously, and we also have discussed about the technologies that involving data warehouse in the previous chapter. So you can check out that video, although there's only one part, there's no part 2. Sorry again. Okay, now we're going to talk about how we're going to integrate all this into one data warehouse, the technologies and everything lah. And more importantly, how do we justify the data warehouse of the future? Okay, now we're going to focus on the future and how you want to design your data warehouse. Okay, and then of course we want to integrate the big data into that. Okay, the focus of this chapter, okay, this is a basic chapter in building the data warehouse and big data. Okay, we want to discuss the, of course, integration of big data and data warehouse, the possible techniques and pitfalls, and where to leverage a technology. How do we deal with the complexity and heterogeneity of the technologies? Okay, all this we're going to discuss in this chapter. Also, we're going to answer a question like what are the performance and scalabilities of each technology and how can we sustain performance for the new environment. Okay, let's start with the content of this chapter. Okay, there are 6 subsection contents in this chapter. So we're going to divide it into 2 parts. Okay, this time I'll make sure there are 2 videos, okay, in this chapter. So for this part 1, we're going to discuss on the components of the new data warehouse. Okay, that's the first session. There are 3 important sections there: data layer, algorithms, and technology layer. And then we're going to discuss on the integration strategies. About 3 also. There are 3 strategies here: data-driven integration, physical component integration, and architecture. Also, last one is external data integration. So after we discuss all the components and the strategies of integration, we're going to discuss about Hadoop and RDBMS. Okay, this going to be discussed in the video, all of this. Okay, this 3 going to be continued in the next video, part 2. Okay, big data process, data visualization, okay, and semantic framework. This will be continued in the next part, in the part 2. Okay, so we're going to start with components of the new data warehouse. Okay, as you can see, this is a figure. Okay, this figure is the components of the next generation of data warehouse. Okay, this figure shows a high-level components that will be the foundational building blocks of the next generation data warehouse, which is the integration of all the data in the enterprise, including big data. Okay, we see the lowest part, there's middle part, and the highest part. Okay, the lowest part here, the lowest part here represent the data. Okay, and this next, the middle part. Okay, this represent the technologies that will be used integrating the data across the multiple types and sources of data. And then the top one, the analytic, okay, that will be the present the analytical layer. Okay, this analytical layer will be used to drive the visualization needs of the next generation of business intelligence analytic. Okay, let's take a look at the first part, data layer. Okay, we already discussed prior to the chapters, okay, about the next generation data warehouse, we have data from across the enterprise that will be integrated and presented to the users for business decision making and analysis purpose. Okay, all this data layer in the new platform will be including all this legacy data, transactional OLTP data, unstructured data, video, images, audio, numerical or patterns or graph, and also social media data, all this type of data. For legacy data, this is data that from all the legacy system and application that include structured and semi-structured formats of data stored online or offline, and it can be integrated into the data architecture. Okay, there are lots of use cases for this data type, like seismic data, hurricane data, census data, urban planning data, and socio-economic data. All that kind of data, that's legacy data. Okay, for transactional OLTP data, okay, this data from transactional system. Okay, so this keyword is transactional system is loaded to the data warehouse. Okay, but due to the scalability issues, transactional data is often modeled such that not all the data from the source system is used in analysis. Okay, the new platform can be used to load and analyze the data in its entirety as a pre-processing or second pass processing step. Okay, this type of data is taken from ERP, CM, and CRM system. Okay, this all kind of data usually left out in processing. Okay, so this data can be used in creating a powerful backend platform that analyzes data and organizes it in every processing step. Okay, that is transactional data. So for unstructured data, for unstructured data, this is most of the content is not analyzed. Okay, there are no standard techniques to create analytical metric on content. Then this is usually the output from processing content data that can be integrated using semantic technologies and used for visualization and visual data mining. Right? I think you're quite familiar with this unstructured data. Means it's not in the it's not very structured, it's not organized. Okay, it's not in a table. Okay, next is video. Okay, data from video usually from the corporation and government agencies, they like to harness into video database. There are three components in a video. Okay, first, the content, the audio, and the associated metadata, and the processing techniques and algorithm for this data type is nascent and complex. Okay, there are that three. Okay, the components in the video. Okay, for the new data platform, however, is provide the infrastructure necessary to process this data. Okay, so that's the importance of the next generation data warehouse. It can integrate this data type and its associated analytic into data warehouse architecture. So this data will be needed as organizations start adopting gamification strategies in customer engagement, government agencies start using the data in managing multiple areas and of defense and security, like image processing, video from CCTV. Okay, and then also weather agencies, they use this data for analysis and reporting. Okay, and the news and media agency use multiple public and private videos to provide education to consumers on real-time and historical news in one mashup. So there is a lot of possibility, okay, on how to leverage the data in commercial and non-commercial aspect. We'll cover in this session. Okay, the video. Okay, so the next generation of data warehouse will be a holistic platform for processing and integrating all these one-off data types for the video. Okay, and next for the audio. Okay, so video is more complex than audio because video have all that three types of data. For audio, the data from call center usually. Okay, we want to extract, okay, from video's contents, want to study on the customers, competition, and many more categories. While the current data warehouse has limitations on processing and integrating data, the new data platform and technology have enabled processing of this data, seamlessly integrating it into the context of data warehouse. So audio data extract can be processed and stored as a contextual data, which are the associated metadata in the next generation data warehouse. That's the importance of the audio data. Okay, and then for images, so images like very useful for especially for healthcare. Okay, like they want to study the X-ray and CAT scans, okay, MRI, everything, and other areas. Okay, image processing basically. Okay, we want to integrate this type of data in data warehouse. Okay, it will provide benefit in a large enterprise. Sharing that such data can result in big insights and generate business opportunities, but non-existent due to a lack of data availability. Okay, basically in healthcare and government agency, very important. Okay, the next one is numerical patterns or numerical or patterns of graph. Okay, this is I think more or less like legacy data. Okay, but all the data that contains numerical can be seen as legacy data as the example, like sex data, sensor data, weather data, stock market data, scientific data, RFID, cellular tower data, automotive on-board computer chips, GPS data, streaming video, and all that data that has a patterns and has a numbers, also have a graph. So there's a lot of it's like infinite of example here. So there's a lot of data for this numerical patterns and graph. So not a combination is all. To process such data and integrating the result with the data warehouse, we provide analytical opportunities to perform correlation analysis, so we can perform cluster analysis or any type of analysis to identify the problem involving this type of data. Okay, so it's very important in integrating the new data warehouse. Okay, last one, social media data. Okay, this one typically classified as all the social media apps like Facebook, LinkedIn, Twitter, Instagram, TikTok, everything that related to social media. Okay, this data is a lot. Okay, it's a big data. Okay, it can be purchased from third-party aggregators such as DataSift, Genome, or Nielsen. And the processing of this data in data warehouse can be accomplished using the rules engine and semantic technologies. Output from this processing can be integrated with multiple dimensions and of the data warehouse. So all these data layers consist of data set. They are most commonly available to organization as they are asset or from third-party sources. Okay. So the non-data set that can be processed today consists of 20% of the data that has been discussed in the data layer. But how do we process the remaining data and how does the integration happen? Right, so to discuss that, we're going to move to the next slide. Alright, next up is algorithms. For algorithms, big data processing needs to happen in the order as shown in this figure. Right, it started. Okay, the first step started with the data acquisition. Okay, this is the process where we want to perform discovery of data. This is where the complexity of processing data lies, especially in unstructured data. To accelerate the reduction of complexity, there are several algorithms that have evolved in commercial or open source solution. The key algorithm, the example of key algorithm is data acquisition, such as text mining, data mining, pattern processing, statistical model, and also mathematical model. I think you have heard some of it, like text mining. in the AI, which is we want to the algorithms. Usually, all these algorithm is available in the open source lah. Okay, like text mining, to process the text based on the user-defined business rules and extract data that can be used in classifying the text for further data expression purpose. Okay, this usually in AI. Okay, and then the next one is data mining. Some more or less like machine learning. Okay, so using the um, algorithm, this data mining algorithms usually to produce data output based on statistical data models that work on population clustering, data clustering, and segmentation based on dimension and time, called micro-segmentation techniques. Okay, the pattern processing, we want to see the pattern from like credit card, POS data, ATM data, stock market signal, sensor data from building, trains, truck, automobile, airplane, ships, satellites, and everything lah. Okay, we want to detect the patterns, okay, in the data. Okay, the pattern data will be processed in transactional manner for that single instance. Okay, the advantage of this data, okay, pattern processing in the data warehouse will help in the ability to tap into this one-time accuracy and the entire data set to arrive at a more defined predictive model or data behaviors. We can predict the data behavior, have a predictive model of the data behaviors. The next one is statistical model. Usually these algorithms used to models largely in financial service and healthcare to compute statistical data for managing population segment. This is very popular method, popular algorithm. This model usually can be developed by using R and others software like SAS, SPSS, and so on. Okay, the last one is mathematical model. This algorithm usually models for some things like disease prediction, weather prediction, fraud analytic, and other non-statistical computes that require mathematical model, ODE, everything. Also, you can use it for the COVID-19 model. Okay. In this next generation data warehouse, the data required by this model and associated computing fabrics are both available within the data warehouse processing layers. So that is data, all this algorithm in this data acquisition, data discovery, data analysis, data processing, pre-processing, data integration, and data visualization. Okay, the next generation of data architecture and data processing activities, we need to include the algorithm discussed in this section to solve the specific categories of data processing and reporting the analytic delivery from data warehouse. Now that we have the data and the associated types of algorithm, before we discuss the integration strategies, okay, let's do a little recap on the technology layer. Okay, the technology layer we already discussed in the previous chapter. Okay, technologies involved in data warehouse, and also in chapter 3 we have discussed technology involving big data. Okay, so combine everything. So we have this list of technologies. These technologies will be mixed and integrated into the heterogeneous architecture. Okay, all these technologies such as RDBMS, Hadoop, NoSQL, MDM solutions, metadata solutions, semantic technologies, rules engines, data mining algorithm, text mining algorithms, data discovery technologies, data visualization technologies, and reporting analytical technologies. So that will be technology layer. Okay, then these technologies will present significant integration challenges in building the foundational architecture for the next generation data warehouse from a solution architecture point of view. Okay, each of these technology listed here, okay, it has own specific performance, okay, and scalability and strength and limitation and everything. So we need to choose a technology that suits with our our data warehouse architecture. Okay, so we know the data. Okay, already know the data layer. We know what is the technology that we're going to use to integrate. So next we're going to we need to know what kind of strategies, integration strategies that we're going to use. Alright, next up is the integration strategies. For this data integration, it is refers to combining data from different source systems for usage by business users to study different behaviors of the business and its customers. Right, we have learned, okay, maybe you have heard the traditional data integration techniques. Okay, this traditional data integration techniques has been focused on the ETL, ELT, CDC, and EAI types of architecture and associated programming models. But in this big data world, however, this technique will need to either be modified to suit the size and processing complexity demands, including the formats of data that need to be processed. Okay, there are two steps in process, okay, that need to be implemented in big data processing. Okay, the first step is data-driven integration. Okay, so we need this data-driven architecture that will include analysis and design of data processing. And the second step is the physical architecture implementation. Okay, which is a physical components integration architecture. So we want to design the integration between these two, data warehouse and big data. So what we need to do is data driven, and then we go to physical components. Let's start with the data driven integration first. Okay, in this figure, it shows the inbound data processing of different categories of data. This model segment each data type based on the format and structure of the data, and then process. Okay, the processes and the appropriate layers of processing rules within the ETL, ELT, CDC, or text processing techniques lah. Okay, so first we're going to take a look at the data classification. Okay, as shown in this figure, there are broad classification of data. There are transactional data that consists the classic OLTP data belongs to this segment. Okay, and then there is a web application data. Okay, where is we obtain the data from the web application. Okay, and then we have the EDW data. Okay, this is the existing data from the data warehouse. Okay, and then we have analytical data. This data is from analytical system that are deployed currently in the organization. Then we have unstructured data. Okay, this is very broad category lah. So we have text, images, videos, social media, audio, sensor data, weather data, scientific data, stock market data. All that data that is not structured. Okay, especially like videos, images, social media, audio, sensor data, weather data also, and so on, like I just mentioned it. Okay, and then we have the last one, semi-structured data. Okay, this include emails, presentation, mathematical models and graph, and geospatial data. Okay, all this type of data. Okay, we go to this processing, and if we go to this semantic technologies, enterprise metadata and enterprise MDM. Okay, next one. Okay, the next one before we go to the workload category is architecture, but it's not in the slide because it's a very short explanation. I'm going to explain about the architecture before I explain about the workload. Okay, architecture, after we discovered, we identified okay, the data, the types of data, the data characteristic or data types, everything. So we can design the architecture based on the data characteristics, data type and everything. Okay, that's architecture. Okay, after architecture, this is what we're going to discuss here, which is workload. Okay, workload is the biggest need for processing big data. Okay, workload management. But we already discussed big data workload management in the previous chapter, so we're not going to discuss that. We're just going to discuss the workload category when we want to integrate this data warehouse and big data. Okay, so for the workload category, there are four. When the volume is low, okay, here, but the time is very short to process data, okay, because of the low latency. Okay, but when we have high volume of data, but shorter time because low latency is simple or complex processing, and then we have a high volume of data, high latency, and simple or complex processing. Okay, because of it's high volume, it's high latency, so it takes a longer time. Okay, the last one is low volume but high latency. So because the high latency is will take some time to process it even if have low volume of data. Okay, the goal of using the workload quadrant, okay, this quadrant, is to identify the complexities associated with the data processing and how to mitigate the associated risk in infrastructure design to create the next generation data warehouse. So that's why we use this quadrant. Right. Okay, the next one is analytics. Okay, this figure. Okay, this figure it shows the analytics processing in the next generation data warehouse platform. The key architecture integration layer here is the data integration layer, okay, which is a combination of semantic, semantic reporting and analytic technologies, which is based on the semantic knowledge framework, okay, which is the foundation. The semantic knowledge framework is the foundation of next generation analytics and business intelligence. This framework, this semantic framework, will be discussed later in this video. Okay, analyzing the data architecture is the most time-consuming task, which once completed will provide a strong foundation for the physical implementation. So this is the foundation. Okay, next we're going to go to physical implementation. The physical implementation will be accomplished using technologies from the earlier discussion. Right. The next generation data warehouse will be deployed on heterogeneous infrastructures and architectures that integrate both traditional structure data and big data into a one scalable and performing environment. Okay, there are several options to deploy the physical architecture with pros and cons for each option. So you have to take a look which option is the best, based on the pros and cons. The primary challenges that will confront the physical architecture include the data loading, availability, data volume, storage performance, can be diverse, and changing query demands against the data, and operational cost of maintaining the environment. Okay, we're going to discuss the key challenge here. Okay, we're going to start with the first one, data loading. Okay, with no definitive format or metadata or schema, the loading process for big data is simply acquiring the data and storing it as files. This task can be overwhelming when you want to process real-time bits into the system while processing the data as large or micro-batch window of processing. And appliances can be configured and tuned to address these requests. In this setup, as opposed to pure play implementation, the downside is a custom architecture configuration may occur, but this can be managed. Okay, continuous processing of data in the platform can create contention for resources over a period of time. This is especially true in the case of large documents or videos or images. If this requirement is a key architecture driver, an appliance can be suitable for this specificity, as the guessing game can be avoided in the configuration and setup process. But release configuration optimization can be daunting in large environment, and the appliance architecture provides you reference architecture setup to avoid this platform. So basically, all this explanation here, you have to think about the loading process, okay, because big data, we're going to deal with the very large data, okay, in the it's either the data is very large or in the micro batch windows. All this data need to be processed, so we want to um, minimize the data loading time. Okay, so in order to do that, we have to figure out the architecture, okay, and configuration. Of course, the suitable platform, since this is a physical components integration. Okay, then we go to the data availability. It also has been a challenge for any system that relates to processing and transforming data for use by end users. And big data is no exception. The benefit of Hadoop or NoSQL is to mitigate this risk and make data available for analysis immediately upon acquisition. The challenge is to load the data quickly as there is no pre-transformation required. Data availability depends on the specificity of metadata to the CD or F4 layers. If data can be adequately catalogued on acquisition, it can be available for analysis and discover immediately. Since there is no update of data in the big data layers, reprocessing new data containing updates will create duplicate data, and this needs to be handled to minimize the impact on availability. Okay. So another challenge is the availability of data. For the storage performance challenge, okay, this performance is an important consideration when building big data system, and the applicants model can provide a better focus on the storage class and tethering architecture. This will provide the starting kit for longer term planning and growth management of the storage infrastructure. So we need to know, so the important consideration is on the disk performance for the storage. Okay, if a combination of in-memory, SSD, and traditional storage architecture is planned for big data processing, the persistence and exchange of data across the different layers can be consuming both processing time and cycles. Okay, care needs to be extended in this area, and the applicants architecture provide a reference for such a complex storage requirements. So if it is combination, you need to make sure the exchange across the different layers take shorter time. Okay, because it usually is consume longer time to do this or the exchange data across the different layers. Right, next, the last one is the challenges that we face is the operational cost, okay, obviously. So when we calculating the operational cost for the data warehouse and its big data platform, is a complex task that includes initial acquisition cost for infrastructure, plus labor cost for implementing the architecture, plus infrastructure and labor cost for ongoing maintenance, including external help commission from consultants and experts. So all these are the costs. Okay, the operational cost is not cheap. Okay, so for the external integration, okay, this figure, okay, this figure here, it shows the external data integration approach to create the next generation data warehouse. Okay, in this external data approach, the existing data processing, okay, and data warehouse platform are retained, and a new platform for processing big data is created in new technology architecture. Okay, so this one is new. Okay, a data bus is developed using a metadata and semantic technology, which will create a data integration environment for data exploration and processing. Okay, a workload processing is clearly divided in this architecture into processing big data and its infrastructure and the current state data warehouse infrastructure. So it's divided into big data and data warehouse infrastructure. Right, the streamlining of workloads helps maintain performance of and data quality, but the complexity increase. okay, in the bus architecture, which can be a simple layer or an overwhelming complex layer of processing. This is a custom-built solution for each system that will be integrated into the data warehouse architecture, and it's a lot of data architecture skills and maintenance. Okay, there are pros and cons in this external data integration. For the pros of the data integration, it's a scalable design for RDMS and data processing. It reduces overload on processing. The complexity of processing can be isolated, and then modular data integration architecture and heterogeneous physical architecture deployment, providing best-in-class integration at the data processing layer. Okay, but there is a cons, of course. I mean, the response pros, there is a cons. For the cons, the data bus architecture can become increasingly complex. Poor metadata architecture can creep due to multiple layers of data processing, and last one, data integration can become a performance bottleneck over a period of time. So this is pros and cons that we need to consider lah, in order to choose which to integrate in our data warehouse and big data. Okay, next is the example use cases for this type of integration architecture. Okay, there are 5 examples of use cases. Okay, first one is data loading is isolated across the layers. Okay, this provides a foundation to create a robust data management strategy. Second is data availability. So it's based on average ranges of data loading, data availability, data volume, storage, performance, and operational cost. So how this type of integration can be organization where the data remains fairly stable over operate time across the data spectrum. Okay, yeah, I think you can just go through each of example of use cases. Okay, just written here. Okay, for data loading, data availability, data volume, okay, storage performance, and operational cost. Okay, for this architecture, the operational cost calculation has file and variable cost component. The variable costs are related to processing and computing, infrastructure and labor costs. The file costs are related to maintenance and data related costs. Right, there are pitfalls to avoid. Too much data complexity at any one layer of processing. For metadata, incorrect data analysis within big data layers, incorrect levels of integration and data quality within the big data layers, and incorrect application of data bus integration. Okay, last in this video. Okay, then the next one, the last one is the Hadoop and RDBMS. Okay, this is the figure in the integration driven approach to create the next generation data warehouse. Okay, to create the next generation data warehouse, so we combine data warehouse. So this is data warehouse part and the big data processing platform. Okay, so this these two connected with the Hadoop and NoSQL connector. Okay, and this connector, this Hadoop and NoSQL connector is will be a bridge to exchange data between the two platforms, between data warehouse platform and big data platform. Okay, for the RDBMS, BI analytics, okay, business analytics, and NoSQLs. Vendors have developed Hadoop and NoSQL connectors. Workload processing in this architecture blends data processing across both platforms, providing scalability and reduced complexity. The streamlining of workload creates a scalable platform across both the infrastructure layers, where the data discovery can be seamlessly enabled in either platform. The complexity of this architecture is the dependency of the performance of the connector. This one is so this will be the complexity. The connectors largely mimic JDBC behavior, and the bandwidth to transport data will be a severe bottleneck considering the query complexity in the data discovery process. Okay, so let's take a look on the pros and cons for this integration. So the pros: scalable design for RDBMS and big data processing, modular data integration architecture, heterogeneous physical architecture deployment, providing best-in-class integration at the data processing layer, and then metadata and MDM solution can be leveraged with relative ease across the solution. For the cons, performance of the big data connector is the biggest area of weakness, and data integration and query scalability can become complex. For the use cases, for examples, we still consider on the data loading, integrity, data volume, storage performance, and operational cost. For data loading, it seems with external integration. So the different here in the storage performance, because in this type of integration we have Hadoop. So Hadoop is designed and deployed on commodity architecture, and the storage costs are very low compared to traditional RDBMS platform. So this is might be a advantage. So people more considered in this type of integration, needed the external integration. Okay, and then for the operational cost, in this architecture, the operational cost calculation has file and variable cost component. The variable costs are related to processing and computing infrastructure, and variable costs, the file costs are related to RDBMS maintenance and related costs. So basically to maintain the RDBMS. Okay, pitfall to avoid: too much data complexity at one layer of processing, executing large data exchange between the different layers, incorrect level of integration at data granularity, and applying too many transformation complexity using the connectors. Alright, I think that's all for this part 1. So we're going to discuss much more on big data appliances on the part 2 video. Alright, thank you for watching.